Hey guys, what's up? My name is Gabe, and this is Games with Gabe. This is the next episode in the Coding a 2D Game Engine in Java series. So in the last episode, what we did was we did sprite sheets. We gave us a way so that we can now get individual sprites off of a bigger sprite sheet that contains multiple sprites jumbled up into there. We can't really use that though. So a nice way to be able to use this is with animations. Now you can have animations because you have multiple sprites, but we have no way to tell the GPU that a sprite has changed. So in this tutorial, what we're going to be covering is something I call a dirty flag system. Basically, all this means is anytime one of the sprites or our game objects is changed, we tell the GPU, hey, something's changed, and then the GPU goes and redraws it and makes it better. So that is the goal of this tutorial. We will get that dirty flag system up and running, and then we will have a way to change our sprites and get some cool animations and stuff going. Let's talk about how this works in a little bit more detail, and then we will code this up. So before we begin coding, let's talk about what this whole dirty flag system thing that I came up with is and why we need it. Well, in order to understand that, we need to understand our game world, right? Our game world has a bunch of sprites, which, as we remember, are just squares with some picture in it, right? That's what our game world is made up of. Now, at any given moment, this sprite could be moving because of its game object, right? Its XY could be changing. We could be changing its color because who knows, maybe it hit something and you want to blink it on and off the alpha. It could be changing its UVs, right? Because all of a sudden its texture ID changed and we need a whole new UV. It could be changing its image completely, which means its ID is now in a completely different texture, which we need to think about, right? Because it's animating, it's changing its images. All these things are things that could be changing, but there is a problem, right? Where are we doing all of this? Where is this all happening? Well, that's happening on the CPU, right? Because our CPU is the one that's running the program, and it's the one that's doing the updates every frame and saying, hey, update all the game objects, and then when the game objects are updated, then all of a sudden the sprite changes because of something in the game object told it to change, blah, 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 blah. But who's doing the drawing? That's the GPU. The GPU is doing the drawing right now, but the CPU is changing a bunch of this data. That means the GPU should be drawing different things, but it doesn't even know that this stuff has changed because it's only being told by the CPU, right? So we need a way for our CPU to say, hey, GPU, we have changed a lot of stuff. Here's the new vertex buffer. Draw this one instead. And then basically the GPU is going to be like, okay, so I am going to draw new stuff now. So how do we do this? How do we keep track of stuff that has changed and stuff that has not changed? And the best way that I have found to do this is similar to how HTML documents update their systems. It's not really similar, but it's the same concept. They have a dirty flag system where if any element on the website has changed, and then they only update that portion, and that's what we're going to be doing. If any sprite in our game world has changed, then we only reload, say this one changed, we only reload his data. We don't care about him because he's the same. That way we have to reload minimal data, and it makes it a little bit better. Hopefully, I haven't done any performance testing, so I don't know how much this will actually speed things up and stuff. But this is the approach we'll take. And the way that we can accomplish this is by basically saying, hey, this sprite is dirty, which means we need to reload his data. So if the position, the color, the text chords, or the text ID, these are all things that are in our vertex data, which the GPU cares about. If any one of those changes, we need to say, hey, the sprite is dirty. Now, where should we do that? Should we do that on the game object? I would say no. The game object itself is just an entity. It doesn't care about how it's being rendered, right? This is all rendering stuff that we're having to deal with. Well, where else could we put it? Do we put some custom flag inside of a whole new component that basically just tells us whether a sprite's dirty? And I would argue no to that too. I think the best place to actually put this is inside of our sprite renderer, right? Because he currently has the position via the game object, the color, because he stores that internally, the texture coordinates, and the texture ID. All this stuff is already contained inside of here. So he should tell us when anything changes. And when something does change, then he should say, okay, I'm going to set this flag dirty to true. I am now dirty because something has changed. And this is just a Boolean variable. It's not an actual flag. Then inside of our render batch, when we are looping through all of our sprites, we can just say, well, we'll have to loop through all the sprites before we actually draw anything. And then we can say if that sprite's dirty, we'll then just reload his data. Then, if any of the sprites were dirty in this whole loop, then we need to rebuffer. So we'll send the data back to the GPU with a GL call. And doing it this way maintains this strict decoupling of the render batch and the sprite render, which is really nice. Notice this communication is happening implicitly rather than explicitly. The sprite render does not tell the render batch explicitly, hey, I need you to change because something has changed within me immediately as soon as this happens. And instead, it implicitly changes a flag about itself. This render batch knows it has to check for these things every frame. And so then it sees and loads it. And so this sort of implicit communication allows us to maintain, like I said, the strict decoupling, which is nice because the more dependencies, the more codependencies you have on your code, the harder it will be to change things in the future. Technically, this is a codependency too, but it's also not, because if we removed this whole dirty flag system completely, our render batch would still work. It would be fine. Nothing would have to change in here. Whereas if we had this calling some function on the render batch, and then all of a sudden we remove that function from the render batch, well, our whole code base is broken. So this is the reason we're doing it this way. Decoupling, it's nice. Okay, one last complication. You'll notice I have a question mark under text ID. Why do I have that question mark? Well, if you remember that text ID tells us what texture we are sampling from, right? Well, if you also remember, I said one texture batch can have up to 8 textures. So say we have 8 textures in batch 1. Say we have another batch, batch 2, that has 2 new textures. So we have 10 textures total that we are sampling from in our game. Say this text ID changes because it has changed textures. But say it was 0 and it changes to text ID 0, but it's actually 0 in a completely different batch. Well, what that means is that this sprite no longer even belongs in batch 1. It used to be in batch 1, but since it's changed textures to a texture that we don't even have in here, we have to completely remove it, then re-add it to batch 2. And that's beyond the scope of this tutorial because that involves deleting vertex properties and everything, which we aren't going to get into just yet. We will get into that in the future though. And when that comes up, we will handle this case where all of a sudden we have sprites moving from completely different batches. All right, now that we have a little bit of this down though, let's actually code it and see what we can get done. All right, so I'm back in the code. Let's go to the first little bit, which will be the easiest part, which is detecting if something has changed. So if we go back into our sprite render, which is actually up here, you'll notice that we have some of these properties as private, which is really good because that means if they change, we will know, right? So the only way that these could change is if somebody calls these new functions that we're about to say. So we'll say set sprite, and then this dot sprite equals that sprite. Then we should be good in terms of texture coords and texture because that data is coming from here too. Then we will have one public void set color, and then we're going to take in a vector for f color, and then we'll say this dot set color, or not this dot set color. We'll say this dot color dot set color, which will basically just copy the RGBA values directly into this vector. So now we have these, and that should be good. That's the only things that will really be changing is the sprite and the color. And then the last thing that's going to be changing, remember, the position. How do we tell if the position has changed? Well, the easiest way to do this is literally just to keep track of the transform. So we're just going to create a variable that says last transform, which basically means this is the last whole transform. So scale everything that was recorded for this sprite. If anything changes on this, we want to change the sprite. That way, if something like the scale properties change or something like that, we also get notified. So let's make this a little bit easier on our lives, and let's go into transform. And let's create a copy method real quick. So we will say public transform copy. This will return a copy of whatever transform this is. So it will say transform t equals new transform, and it's going to use new vector 2f this dot position, and new vector 2f, this dot scale. This, by passing in a vector to a new thing like this, it will just copy the contents into a completely new vector. That way we don't get any problems with different things. Okay, so then we'll just return t. So we make a copy of it and we return it. And it's going to tell us we can actually inline this, which is nice. Yeah, saves an instruction or two, which is cool. And then we will make one more function, which will make our lives easier too. We will say public void copy transform 2. So this one will copy the contents of this transform, so this to 2. So it just copies itself to whatever we pass in. So then we'll say 2 dot position equals, actually we'll say dot set this dot position. And what that will do is it'll just copy the x and y to this, to whatever is in here, right? So set basically takes in this and then it puts these values into this value. So it just makes them the same. Then we'll say 2 dot scale dot set this dot scale. There you go. And these two utility functions will be very nice to have. Let's go back into our sprite render now. And we have this variable last transform. Inside of our start method, we want to get a hold of that last transform. Remember, we can't do it in here because if we try to say this dot last transform equals GameObject dot transform, we would actually copy it. But if we do this, GameObject's could be null right now because there's no way we can have a reference to GameObject inside of our constructor. The whole reason we have the start method is that we can access the GameObject. So we'll say this dot last transform equals GameObject dot transform dot copy, which will copy the transform into our transform. Now we have a copy of the transform, and inside of our update method, we want to check and see if that ever changes. So let's actually go into transform. We will do one more method real quick. This is a method every class has, which is public boolean equals, and it takes in an object O. This method is exactly as it sounds. It just checks and sees if this is equal to O. So what we'll do is we'll say if O equals null, return false. Definitely doesn't equal it. If O not O instance of transform, return false. If it's not a transform, then there's no way it could be equal to this either. Then if both of those are true, we'll say transform t equals transform O. We know it's safe to cast now because we've checked that it is a transform. And then we'll just say return t dot position dot equals this dot position and t dot scale dot equals this dot scale. So now we can check and see if two transforms are equal. This will check and see if they have the same position and scale, which means it is the same. So inside of here, we can say if not this dot last transform dot equals this dot GameObject dot transform. So if the GameObject's transform has changed in any way, its position, its scale, whatever, then we will know because this contains the last transform that it was. So if that did happen, what we're going to do is we're going to say this dot last transform. Actually, we're going to say this dot GameObject dot transform dot copy, and we're going to copy it to the last transform. So we'll copy that data, and then we will set our flag is dirty equals true because something has changed. So let's go up here now. We'll say private boolean is dirty equals false initially. So we know that we are dirty now because something has changed. Also, let's go into here. This dot is dirty equals true if they set the sprite to something new, and if they set the color, of course, it's also going to be dirty. And let's actually be a little bit more wary. We don't want to set to dirty if they just do this. We'll say if this dot color dot equals color. So if they are not equal to each other, then we'll set it to true. And in fact, let's not even copy it. So if they're just trying to change the color and it's the same color that it already is, there's no point in even setting the color because it's just the same thing. And then we'll worry about sprite another time because this contains a little bit more data than I'm willing to work with. And this is fine for now. We'll just set it to dirty every time the sprite is changed. But yeah, that should now set a sprite to dirty if any of the data that we care about has been changed, minus the sprite, of course. Well, I mean, it will set it to dirty. We just aren't checking to see if it's the same sprite that they're trying to set it to. But that's good enough. Let's go into render batch now and actually implement our check so that we check and see if any of the sprites are dirty and we fix it if they are. So up here, we'll go to our render method. Before we actually bind the buffer, and actually we're buffering all the data anyways every frame, which is good, but nothing is changing in here, right? So before we do that, what we're going to do is we're going to say for int I equals 0 till I is less than sprites dot size length I plus plus. So we're going to loop through all the sprites. Then we're going to say sprite render SPR equals sprites I. Then what we will say is if SPR.is dirty, and we will get a function real quick for that. So we'll go into here and we'll just say public boolean is dirty, return this dot is dirty. Then let's also do public void set clean, this dot is dirty equals false. So we'll have a clean method too. So back into the render batch. If the sprite is dirty, first of all, what we're going to do is we're going to say load vertex properties I, then we can say sprite.setClean. And then let's also have a flag up here. We'll say boolean rebuffer data equals false. Then if any of the sprites are dirty, we'll say rebuffer data equals true. Then down here, we'll say only if we have to rebuffer the data should we do this. And then we will copy that. I'll get rid of that since we are not doing it every frame now. So that's pretty simple, right? We already have this function load vertex properties that does everything we need it to do, right? This is the reason also that I abstracted this into a function, because this is really nice now when we need to rebuffer data. So this basically just finds the sprite that we're using right now, and then it loads all the appropriate vertex data because we did all that stuff already. So now we can reuse that functionality in here and say if it's dirty, then we need to reload that data once again. Then we just say, okay, now that sprite's clean, let's rebuffer the data now. That way, the next frame comes around, if it hasn't changed, we won't rebuffer it again. Then we just check and see if we have to rebuffer any data. And if we do, we buffer the subdata, which is really just the whole vertex array for now, which is also fine. Let's check and see if this is actually working now. Let's go into our test scene or our level editor scene. And inside of update, I have this camera movement thing, which I don't know if I ever went over that, but get rid of that. And let's make object1 a variable that is global to the class. So we'll go up here and then we'll just say private game object obj1. Then inside of our update method, what we'll do is we'll say obj1.transform.position.x plus equals 10 times dt. And let's see if he starts moving. So we'll go back up and we get an error. So what's happening here? This was a dumb mistake of me. So I said if for int I equals 0 till I is less than sprites.length, that's not actually how many sprites we have. We only have number sprites of sprites. So we should actually loop until we reach the amount of sprites that we actually have in there. So let's do this one more time. And look at that, Mario is moving. This is really cool, guys. This means that we can now do a lot of stuff that allows us to build a game, basically. And you'll notice that he's actually like slowly disappearing. That's because, let me actually show you this too, because I don't want you guys to think you have bugs in your code or something. This is totally okay. If we go to the window and we change the clear color from black, we'll change it to like a soft red. So I'll just do like that and then something like that. So if we change the clear color, we'll notice something. Look how the black behind Mario, this is actually all the alpha values, right? This is where it should just be disappearing, right? Because we have a texture that has some alpha, but our game engine currently can't handle alpha values. The reason being is because of something called blending, which we will get into actually probably in the next tutorial, because that's a good segue. So yeah, we'll do that in the next tutorial, but that is not a bug in your code. Let's go back in a level editor scene and do one more thing that I think would be cool. Let's do a little animation real quick, because we do have the ability to do that. So I'm just going to go up here, say private int sprite index equals 0, private int sprite flip time equals 0.2f. That's a float, and I said that was an int. And we'll say private float sprite flip time left equals 0.0f. Then inside the update method, this is basically just going to be a little animation of Mario. We're going to say if sprite flip time left is less than 0. We'll actually do less than or equal to. Then we're going to say sprite flip time equals sprite flip time left, and then we're going to say sprite index plus plus. Then if sprite index is greater than 4, sprite index equals 0. And we are also going to, in here, say obj1 dot set dot get component sprite render dot class dot set sprite, and we will say sprites dot get sprite, I think we called it, I. And then let's go into, or actually sprite index. Let's go up here and make the sprite sheet a global variable to our class too. So we'll say that sprites, and this is all just test code too, so don't worry about how it works necessarily. I mean, we're just moving the sprite across every 0.2 seconds. Oh, and this is backwards. This should be sprite flip time left equals sprite flip time. There we go. And then this should basically flip Mario so that he's doing a little animation. Let's see what happens. So he's in this pose and then he's not changing, which is not right. Oh, and then we have to do one last thing. We'll say sprite flip time left minus equals dt, so that we actually move it according to how much time has passed each frame. There we go. And look at that. We have a little animation. Mario is running, and he's not really. We're switching the sprites, which is how you would do an animation. So that's a cool little thing that we got done in this video. Now that we know how to rebuffer all the data and everything, that's about it for this tutorial. In the next tutorial, like I said, what we will be going over is alpha blending. Like I said, this series, we are doing a lot more stuff manually than we have in the past. And that includes how we actually blend the alpha, which I will explain in much more detail in the next tutorial. I hope you guys like this. If you did, please hit like and subscribe. And I will see you guys in the next episode. See ya.